Hello, this video includes information on types of solids.
We're going to deal a little bit with different types of solids. So when we look at solids, one type we might see is called a crystalline solid. And when we look at crystalline solids, they have a very regular pattern to their arrangement. And the pattern is made up of what are called lattice positions. And the smallest repeating unit is called a unit cell. So we also have what are called amorphous solids. And the prefix a before word means without, and morph means shape. So we're looking at solids that have an amorphous type of a shape. Okay, they kind of have a disorder to their structure. Okay, they may undergo transitions to become crystalline under appropriate conditions of temperature or pressure. And they have no basic repeating unit or no unit cell. So looking at examples, this is kind of a picture depicting a crystalline solid, and this would be more of an amorphous solid. And when we look at crystalline solids, talking about sodium chloride, that's like a classic example of a crystalline solid, or quartz is an example of a crystalline solid. As opposed to amorphous ones, glass and candle wax are two less ordered types of solids, or amorphous solids. And we're going to spend just a little bit more time talking about the crystalline solids and these unit cells. So when we look at a unit cell, okay, a crystalline solid is described by the simplest repeating unit. And that repeating unit is called our unit cell. And when we look at the unit cell, the points of the unit cell are called our lattice points. So if this is the crystalline solid that we're looking at, okay, this would be the repeating unit, or the unit cell. And the unit cell is made up of these points here, which we call lattice points. There are different types of crystalline solids depending on what's found at the lattice points. So if we talk about crystalline solids that have ions at their lattice points, we call them ionic solids. So as an example, sodium chloride is a crystalline solid where the sodium ions and the chloride ions are at the lattice points. When we talk about atomic solids are a type of crystalline solid that have atoms at their lattice points. So carbon or boron or silicon at these lattice points would be an atomic solid. So having carbon could mean we're looking at diamonds. And there are two types of atomic solids. There are metallic solids, which means that we've got metal atoms at the lattice points, or they can be network covalent solids. And the third type of crystalline solid would be molecular solids. And molecular solids have molecules at their lattice points. So it's pretty easy to figure these out. Ionic solids, atomic solids, and molecular solids are all crystalline solids that have those unit cell repeating units within them. And the lattice points are identified by the name of the solid. So ionic solids have ions in them, atomic solids have atoms in them, molecular solids have molecules in them. So let's look at ionic solids in a little more detail. So we're going to be looking at ions in the lattice points, and they're held together by electrostatic interactions. Essentially what that means are the positive ions are attracted to the negative ions. Ionic solids are classified as having high melting points. they're hard and brittle, and they can't conduct an electric current when they're in their solid state. But if we were to melt them, okay, make them molten, or if we were to dissolve them in water to loosen up those ions, then they would be able to conduct an electric current. Okay, so we're looking at sodium chloride. This would be kind of a depiction of what that sodium chloride molecule would look like. If we were to look at calcium fluoride, we've got a little bit of a different look to the unit cell. And then we could look at iron sulfide, which is fool's gold, which has an even different type of unit cell. So atomic solids, we've got two types. The first type are metallic solids. So that means we've got metals at the lattice points. And the way that they are formed is we have metal atoms at the lattice points, and the electrons kind of surround those metal atoms. They're delocalized electrons. They're not attached to one atom or identified with one atom. Sometimes it's referred to as like a sea of electrons. So the metal atoms are kind of embedded within a sea of electrons. And we say that those electrons are delocalized, or they're non-directional. This gives us a little bit different picture here. We've got the metal ions here, and then we've got the sea of electrons around them. So those electrons are not localized to a particular atom, but they're kind of spread out throughout the structure. Okay, metals, atomic solids made out of metals with their lattice points are very hard and strong, but they are malleable and ductile. So malleable means that we can kind of spread them out into thin sheets. We can hit them with a mallet and make them nice and thin. Ductile means we could draw them out and make wires out of them. And metals are malleable and ductile because of the way that the atoms are arranged in that atomic solid. Okay, their melting points can vary. Some of them are higher, some of them are lower, depending on the type of atom and the attraction of those ions to the electrons. The second type of atomic solid are network covalent solids. So when we look at these, we're going to have atoms at our lattice points. The atoms this time aren't going to be metals, but they'll be non-metal, something over on the right-hand side of the periodic table. And they're held together by networks of covalent bonds. Okay, because the covalent bonds are pretty strong, okay, they typically are hard, strong, and have high melting points. So we have a couple of examples here of atomic solids made out of a network of covalent bonds. So diamond might be an example, silicon dioxide is an example, and so forth. So they're a type of atomic solid, but this time the atoms are non-metals, which are held together by a network of covalent bonds. Okay, so graphite and diamond are two examples of these network solids. So when we look at graphite, okay, graphite is a planar network solid. Okay, it's flat. It's got 6-membered carbon rings. So this is kind of an appearance of what graphite might look like. Each carbon atom is bonded to 3 other carbon atoms. And graphite is good at conducting electricity. Okay, the electrons can easily flow through graphite. And we've got kind of 2 different things going on. We've got interactions within these planes, okay, which are very strong. But then we've got interactions between the planes, which are weak. So if you look at a pencil, okay, a pencil isn't made out of lead, even though they say it's made out of lead. The stuff that we write with out of a pencil is actually graphite. And it's just those planes that slide past each other as it writes on the paper. So if we look at diamond, okay, diamond is a 3D network of carbons, 6-membered carbon rings in what's called a chair conformation, but you'll see that more when you go into organic chemistry, if you take that class in the future. Each carbon is bonded to 4 other carbons. It's denser than graphite because of the way those carbon atoms are arranged. And it can't conduct an electric current because the electrons are localized, or they're kind of assigned to specific atoms, and they can't flow through the substance. Okay, diamond is very hard because of those network covalent bonds. They're good conductors of heat. And they are transparent to visible UV and infrared radiation. There are some solids that are 1 atom thick solids. Graphene is a good example. It's strong, it's lightweight, and it's really good at conducting electricity and heat. So it's been used in computer chips and circuits, and to make batteries better, and for solar cells. And this is a really up and coming type of a research solid that's used in lots of different kinds of applications. So when we talk about molecular solids have molecules at their lattice points. And the molecules are being held together by intermolecular forces, either the London dispersion forces or the dipole-dipole forces or the hydrogen bonding that we talked about before. So if we were to look at carbon dioxide, okay, carbon dioxide might be an example of a molecular solid where the neutral carbon dioxide molecules are at the lattice points. Iodine could be an example, I2 being at those lattice points. When we look at, let's say, ice, okay, ice is an example of a molecular solid where those H2O molecules are at the lattice points. Or if we were to look at table sugar, okay, that has sugar molecules at its lattice points. So to kind of summarize all of that up, again, we've got kind of 2 categories of solids. We've got crystalline solids and we've got amorphous solids. Crystalline solids are made up of very organized repeating patterns called unit cells. And unit cells have those lattice points. And depending on what's in the lattice point determines the type of solid we're looking at. So we've got ionic, we've got atomic, and we've got molecular. Okay, ionic is when we have ions at our lattice points. Metallic and network covalent is when we have atoms at our lattice points. And molecular is when we have molecules at our lattice points. That kind of just summarizes that all up. All right, so let's just look a little bit more at those unit cells, and then we'll move on. We'll be done with chapter 10 and go on to chapter 11. So when we look at crystalline solids, okay, they have those unit cells that are used to describe them. They're classified by what their unit cells look like. And the unit cells are basically of 3 different types. Okay, we have what are called simple cubic, body-centered, and face-centered. Okay, so simple cubic has 4 atoms on the top and 4 atoms on the bottom of the the unit cell. Body-centered has an atom in the middle, and then it has along the lattice points. And then the face-centered actually has ones along the lattice points and ones along the sides or the faces of the unit cell. So when we talk about efficiency, okay, how well the atoms are packed into the unit cell, we would just take the volume of the atoms and divide it by the volume of the whole cell and multiply it by 100. And simple cubic systems, simple cubic unit cells are the least efficient, only about a little more than half of the space in the unit cell of a simple cubic system is actually made up of particle. About half of it is made up of empty space. When we talk about the unit cells, one of the things that's considered is what's called the coordination number. And the coordination number is just the number of atoms that are coming in contact with the atom that we're looking at. And for simple cubic systems, the coordination number is 6. So if we're looking at a simple cubic unit cell, and this is our cell here, or the cell of interest, it's connected to 1, 2, 3, 4, 5, 6 other atoms. So the coordination number is 6. So this is another depiction of just the unit cell itself. So if we look at a simple unit cell, again, we have an atom here, 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 and here on the top, and then 4 on the bottom, but only a fraction of that atom is actually part of this unit cell. Okay, some of it's going to be in the cell above and the cell on the side. Okay, if we look at this one here, again, we've got the corner points, but we've got the central atom as well. And if we look here, we've got the central atom, but we also have corners and we have sides. So if we wanted to analyze a unit cell, okay, let's say this is the unit cell that we're looking at, the repeating unit of sodium chloride. Okay, and this is our unit of interest here, okay, our atom of interest. Again, the coordination number is 6. 1, 2, 3, 4, 5, 6. Okay, and the kind of bluish colored circles are sodium ions and the greenish ones are chloride ions. What we would notice is that this sodium here is in the center. So this ion here, the whole thing is part of the unit cell. If we were to look at the ones that are on the sides or the faces, we're essentially cutting that ion in half. Half of it would be associated with this unit cell. The other half would be associated with the unit cell next to it. If we were to look at the edges here, okay, those are going to be divided into quarters. 1/4 of this sodium ion is associated with this unit cell, but 1/4 would be associated with the unit cell next to it, and 1/4 would be associated with the 2 that are below it. So this ion gets divided into 4. So this unit cell would only have 1/4 of this ion. If we were to look at the corners, okay, the corners actually get cut in 1/8. So this unit cell only has 1/8 of this chloride ion. The other 7/8 would go with the unit cells that are adjacent to the unit cell of interest. So if we were to look at it in this case here, way inside here, we have a sodium ion that would be counted as 1. If we were to look on the faces, we have 1 on the top, 1 on the bottom, and 4 along each side. So there are 6 on the faces of this unit cell. And each of them is 1/2 of the chloride ion. And then if we were to look at the corners, okay, the edges are the edges. The edges are 1/4 of each sodium. And if we were to look at the chlorides, they're 1/8 of each chloride ion. So looking at sodium chloride, okay, we have 6 faces, 1 on the top, 1 on the bottom, and 4 around the middle. And we've got 8 corners. So for chloride, we've got 6 faces, and 1/2 of each chloride is within that unit cell. So that gives us 3. We've got 8 corners, and each of them has 1/8 of a chloride. So that gives us 1 chloride. So this unit cell has 1 chloride in it. If we were to look at the sodiums, 1 of the sodium ions is in the middle. And 12 of them are along the edges. So 1/4 of 12 is 3. 3 plus 1 gives us 4. The ratio of chloride to sodium is 4:4, or 1:1 in our unit cell. So when we go to count atoms in a simple cubic, which is what we have here, we have 8 corners, and 1/8 of each corner is in our unit cell. So we have 1 atom or ion per unit cell. If we were to look at a body-centered cubic unit cell, we have almost the same thing we had for the cubic, except that we also have that atom or ion in the center. So the total number of atoms that we would find in a body-centered cubic unit cell is 2. And if we were to look at a face-centered unit cell, there isn't any atom way in the middle there of that unit cell. But there are 8 corners, each containing 1/8 of an atom or an ion. And there are 6 sides, each containing half of the atom or the ion. So a face-centered unit cell has 4 atoms in it. And that kind of helps to show why the simple cubic unit cell is the least efficient, whereas the face-centered cubic cell is the most efficient way that atoms or ions are arranged in a crystalline solid.